Okay, so I would like to just briefly talk about this idea of standard deviation. So let's say that I took a bunch of measurements and I wanted to look at students' grades in a particular class somewhere in the United States. And so I might be measuring how many F's, D's, C's, B's, or A's, right? And I could put the numerical numbers down there, right? But I'm going to use just letters to simplify it for now. But we know that there's a scale, right? You can have a low D or a high C, right? Et cetera, et cetera. And so students would fall at various places within that. So if I took a group of students and I just started putting them onto my scale here, right? Let's say the first one's got a B, the next two have A's, right? The next one has a C, somebody over here has an F, unfortunately, D, another C, maybe another B, another C, right? So if I just start filling this in, right, we would expect, and it probably wouldn't happen as perfectly as what I'm drawing here, but we would expect to see a shape like a bell curve emerge. So here I have my poorly drawn bell curve, but you get the idea. So average grade should be in the middle, and we have a name for this average grade. We call it the mean. Okay, so this symbol, the X with the line above it, is the mean. And then we would expect to find about 68% would fall within what we call one standard deviation from the mean. Right, so one standard deviation below or one standard deviation above the mean. Okay, and then we would expect that another standard deviation from the mean would encompass about two standard deviations from the mean. Two standard deviations, then, should encompass about 95% of all of the measurements in that population. So we're still going to have some outliers, right here and here. So there'll still be some samples that won't fall within two standard deviations, right? We could go 3 standard deviations from the mean. But in statistics, a lot of times we're concerned with looking at either 1 standard deviation or 2 standard deviations from the mean, because we're interested in where most, 95% of the measurements within that population fall, for various reasons that we'll talk about a little bit more. Okay, so here's the document that you should be reading if you haven't yet as your homework assignment. I am not going to go through all of this because that's your job. But let's just say it is a creative story that tells how Huck Finn and Tom Sawyer have learned how to calculate confidence intervals. So you can do this yourself. I've already introduced these two terms, mean and standard deviation, so hopefully you understand what those mean by now because those are important in our calculations. Here is that bell curve, right, that shows 1 standard deviation, 2 standard deviations, or 3 standard deviations from the mean here. And here is the practice problem that I would like to go over. So it says the data in the table come from an experiment where they added a predatory ant-eating beetle to a trophic system, right? This is just the food chain in an ecosystem. Starting with the thing at the bottom that's being eaten, right, which is this tiny little seedling, a piper tree. So just to give a quick visual example of what they're experimenting on in this problem. They have a seedling, which is just a baby tree. And the leaves of this baby tree get eaten by some sort of herbivore. Possibly a little caterpillar eating the leaves from this tree. And then within this ecosystem, there is a predator of the herbivore that is a type of ant. And then in their experiment, they introduce one more animal to the ecosystem, which eats the ant and is a type of beetle. Okay, so now you kind of have a visual of what's happening in this ecosystem. They have their control, and then they have the area that they added the beetle to. And they took measurements in 10 different areas, 10 different plots, and they're measuring in centimeters squared, or how much leaf area is being eaten. So I like to use Microsoft Excel to do some of these calculations for me. I can show you how to use Excel to do some of these calculations. You could take out your calculator and you can add up all these numbers and divide by the total number in the sample, which I believe was 10, right? I'm just going to let Excel do it for me by coming up here to this button and choosing average, because that's what mean is the average. And then I'm going to highlight the numbers I want the mean of. And then there's this cool little thing I can do where I can drag this over and it does it in this other box. And so, voila, I have two means. I have a mean for the control and I have a mean for the beetle added area. So here's what we're always kind of trying to determine when we do experiments. We want to know, like if you were to do this experiment and you looked at your numbers and you said, okay, I have a mean of 250 and I have a mean of 145. Are those numbers different? Well, yes, 250 and 145 are not the same number, but are they statistically different from each other, right? Or could they have happened if I had just gone out and tested two separate areas that were both the exact same condition, that neither of them had the beetle added to them? Could one of my means have been 250 and the other mean have been 145? And this is why we want to go and look at our two standard deviations from the mean. We're going to calculate what we call confidence intervals. And so that way we can be confident that the results that we get would fall within two standard deviations of the mean. And we do this by calculating 1.96 by the standard deviation, which in this case it's already been calculated for you. And then we divide that by the square root of n. And n is the number of samples that we have total. So in this case, there were 10 plots in each group, so n would be 10. So we're going to do those calculations now. So my 95 confidence interval for my control would be calculated by 2 times standard deviation over the square root of n, which in this case is 2 times 40.1 over the square root of 10. Because remember, n is the number of samples. And we can do the same thing over here. 2 times the standard deviation, which in this case is 30.6, over the square root of 10, because there were also 10 samples in that group. And if I do this, I should get about 25 for my control and about 19 for my experimental condition where the beetles were added to that area. Okay, now that we have calculated our confidence intervals, now we put them on a graph. So we have to prepare a graph. In this case, it's going to be a bar graph, which in most cases, when we use confidence intervals, we will have bars. And so on my y-axis here, we are measuring the mean leaf area. Remember, that was in centimeters squared. And then we had two different conditions. We had our control, and then we had our beetle added. Condition down here. And let's say I'm measuring in units of 50. And of course, your graphs would be created using graph paper or using a computer program if you prefer. I am limited by this program that I can use so that I can draw it while you guys watch. And so mine is not going to be as nice as yours. But here's what I have. And if you remember, the control was a mean of 250, and the beetle added group was a mean of 145. 250 is about here, and then 145 would be somewhere around here. So once again, you could look at these bars and you could say, well, that looks different, right? Those bars look different. But here is where the confidence intervals come in. So we are going to add confidence intervals that are equal to 40.1 here and 30.6 over here. And so what that means is that I'm going to start at the top of the bar and I'm going to go up 40.1 and down 40.1, and I'm going to draw little bars on it, and that's my error bar. And over here I'm going to do it for 30.6, so my error bar is going to be a little bit smaller. So just a quick correction to the confidence intervals I just put on the graph. When you complete your graph, it's actually going to look more like this. The confidence intervals will be smaller because I calculated those earlier, and then accidentally on the graph I just gave you as an example, I put the standard deviation. And so you can see here that your values for the first bar should fall between 225 and 275, and your values for the second bar should fall between 126 and 164. And I'm going to go back to the original graph because this actually doesn't change our results at all. And so just keep in mind that your error bars would just be a little bit smaller than the ones that I'm drawing on the example problem that's coming up. So I just put my 95% confidence intervals on the graph. And you can see that the error bars, right, the green bars there, do not overlap with each other. So what that means is the bottom of this mean right here, of where this mean could fall, does not overlap with the top of this mean right here. Another way you could look at it is if we were to do this experiment 100 more times, then 95 out of 100 times, the mean for our control should fall between this value and this value. And the mean for the beetle added group should fall somewhere in this area right here. And since these error bars, like I said, do not overlap with each other, there's this area here where there's definitely a difference between the top of this mean and the bottom of this mean, we can say that these two means may be truly statistically different from each other. But if we would like to do an actual statistical test, like the t-test, which you're also going to learn about soon, then that will give us an actual value to determine how statistically significant these means are from each other. This gives us a nice visual representation of that.